My name is Ruben Verhack. I co-founded Datameister about 2 years ago. I have a strong background in computer science. I double PhD in 3D representations. Over the last few years, we've been looking into how actually bringing this more into applications. I'm going to present here a case that we did on AI-accelerated automotive design. And the idea is, starting off with a question: what do these artworks have in common? So first one is Guernica by Picasso. Second one is the 18th Sonnet by Shakespeare, and then we have the David by Michelangelo. The idea is that Picasso had actually could have drawn this in any style that he wanted. He could have done it in a realistic way, but he chose to limit himself to like a cubist language and limiting himself in the types of shapes and forms. Same for Shakespeare. He could have conveyed his information in any free-form text, but the beauty is in the fact that he fitted it in this kind of like sonnet, strict, disciplined manner. And the same for Michelangelo. He did this whole thing in marble. And the fact that like he constrained himself to keep himself fixed to this medium is actually what makes it into a masterpiece. Brings me to the point that a masterpiece is a combination of talent and constraints. Okay, but what about the following? This is the typical AI slop that everybody has been seeing in their feeds for the last few years. And why don't we perceive this as masterpieces? Because technologically, it's great that we can do this. But because it's so easy and there's so much freedom and there's no constraints, you typically fall down into clichés. Because despite there's been like a huge, enormous investment in general purpose visual AI, it doesn't really immediately lead to masterpieces. This is because like an AI, when given too much freedom, it falls back to clichés. It has this kind of knowledge of, like a mean knowledge of what something should look like. And when AI is unconstrained, it tends to do the obvious. However, in reality, constraints shape all design. Especially in industrial design, you have hard points. And hard points are fixed constraints in design these can be physical locations or the dimensions of the objects or rules that cannot be moved or changed without major impact. You don't want to be creative on these things. In automotive, for example, this is when you start designing something, a car, you typically already know what wheelbase you're going to use or other package data. And then there's also a ton of regulatory constraints that you need to adhere by. Same for architecture. You need to take into account some load-bearing structures or elevator shafts or any characteristics of the plot of land you're working on. And also in consumer electronics, you're going to buy some off-the-shelf components. You want to design around those things that are already known. So for example, where the batteries are or any cooling zones. And so the goal is to explore the creative in-between space shaped by these constraints. And this brings us to a project that we did with Gran Studio. Gran Studio is a car design company from Torino. They're known for designing Maserati, like this Dallara supercar, and Alfa Romeo. They saw the rise of AI, image generation, and they saw their clients even like bringing ideas of like, hey, I think it around with Midjourney. This is something I would like to have, but the problem is that these AI generations they start from the surface, whereas actually design starts from the inside. For example, in a car, the position of the engine, where the people need to be, and the steering column, they all matter. Just by changing the type of engine, it has a complete influence on the exterior look of the car. If the engine is in front or in the back, or if you have a four-wheel drive, it will define largely how your car will look like. So Grand Studio, they have developed this hardware product. It's a kind of a creative platform where that completely aligns the digital and physical world. So it's a seating buck that's completely configurable. So the seats can be changed in position. The steering wheel can be completely changed. And this allows you, as a designer, to actually experience the design that you have in mind that you've up till that point only done virtually, and you can add some other props to it. So that it serves as well as like a great communication platform between the stakeholders, the designers, the engineers, the clients, and you can functionally test the car. So you can step into it, you can feel how far is everything, like, do I like this form of interacting, how the feeling of like getting into the car. This is something you cannot do with a clay model. So this is what they already had. So this Digify product, it's a fantastic platform for creative design. Plus it helps to define these hard points, these things that are then fixed. Plus, it actually already largely defines the general shape of the vehicle. I don't know if you can see it, but like just by repositioning these seats and how high the platform is, you can already kind of tell if it's going to be an SUV or a compact car or a delivery truck. So the need is to AI accelerate the ideation process. So now that you have these hard points and you want to kind of design the exterior, that would be really great. And then you have all these AI image generators. But the problem is that these AI generators, they create cars that are not manufacturable. They ignore all these real-world constraints. Plus, they lack practicality. Typically, it's harder to iterate on your design. You often hit this kind of 80% there thing, but like actually closing that last 20% is always the problem. And the results are typically not edit-friendly or not in the form that actually the client wants it. So our first take on this was basically use the AI generators and adapt them to the fixed geometries. So on top left, you have then what we call style input, like an AI-generated image where they were happy about the general style, look and feel of the car. And then you had like a basic geometry of the car that adheres to this Digify data, like a general rough outline of the car. We would then develop a sort of a Blender interface where you can put like a camera viewpoint on this base geometry and to then transfer this style information but onto actually the geometry that is allowed, that you know 100% sure, like, this is something we can make. This already allowed us to iterate on the designs. You could like take regions and regenerate them, but keeping the style intact, but like allowing for like creative exploration. So here you have 3 different fronts, so each time with different kind of lights, different feelings, and then this you can steer with other control signals. You can also, for example, control the atmosphere, because for their clients it's also important. Like if the client is in a more desert country or in Scandinavian country or in more urban environment, you want to quickly visualize these ideas that you have, because this is what it's about. It's still in this ideation phase. Now, the problem here is that, for example, in this case, we start off with like a more of a brake vehicle, and you want to map it more onto an SUV type of geometry. You will start to see that this method starts to break. 2 problems. The first is the fiction before physics. So you first dream, and then you try to retrofit it onto reality. And this will always kind of break if what you've imagined is too far away of actually where you want to land. And the second problem is that there's this tension between geometry and texture, and that which we completely ignored in this first version, because the base geometry was in this case completely fixed. But actually what you want is that these style ideas of, for example, the light catcher, these indents, actually should trickle to the geometry, but that actually doesn't happen at this moment. So we thought of a better way, as basically by constraining a 3D generator. And I'm going to use a toy example, but a literal toy example, where we thought, like, oh, let's make a banana copter. And so we drew a banana, some blades. We defined it with GPT just to get a good starting image. And we then built further on Trellis, a new open source model for 3D generation. These typically always work in the same way. You have a 2D image input, typically multiple images. You encode this into a latent space or a model, like an abstract representation of what the 3D geometry is. And then you can decode that into a 3D output, which is typically a mesh or Gaussian view or some views, so that you can minimize the reconstruction error. You want that the 3D output looks as much as your 2D input. And the way that Trellis operates is, so you start off with your input data, and then you have your generative model, and it has put a three-dimensional structure in this latent space. And that is the big clue in Trellis, whereas in most generative models, this latent space is kind of one big abstract fingerprint of your geometry, but the stuff is not localized in 3 dimensions. Now it is. And this one decodes into Gaussian splatting decoder, which gives you the views and the texture, or you can decode it into a mesh, which gives you the mesh. So this was the base method that we worked on. And to recap, the benefits of this structured latent space is the fact that, like, you have your latent space as a voxelized method, which is basically a compressed version of your 3D space. And every voxel is actually one local geometry and texture descriptor. So this is not the resolution that you can decode in. This is the resolution where your data is modeled on. The cool thing about this is that it's completely differentiable. So this means that we can plug in all the advances of even 2D generative models now into the mix, which helps us to actually completely constrain this whole generation process. So for example, we want to use an off-the-shelf component. We want to buy the blades and the engine, but we want to design around this component. Second constraint is we know how big we want our helicopter to be. So we defined the boundaries. We kind of inject these constraints right into this latent space, which we then call the constraint structured latent space for regions where we allow the optimization to take place or not to take place, or with some weights or with separate control signals. This still then decodes into 3D representations such as a Gaussian splat or as a mesh. And as you can see here in the mesh reconstruction, this is the exact component coming back. This is not like a regenerated component or something. This is the exact constraint that we want to put in. Plus, we can add more stuff to the mix. Like if we draw on one of the output images that we want to have actually to write DM on there, we can force it to update the texture so that it actually gets updated onto in this structured latent representation. But we can also do the opposite. If we can add geometry to it. If we, for example, draw a landing gear as extra, we can have it actually just kind of add this as extra geometry. So this gives us a method which is like controllable, like iterable design method. So you have fixed components that you can use. The dimensions were set. You can update the texture. You can update the geometry. And this is just like the start. This is just the toy example. Okay. Bananas, cars. Let's go back. So where we had the style input image and the base geometry, we can now actually update the geometry, and we can choose where to actually update the geometry. Where I didn't point it out the first time, but you have the spoiler on the back of the stylized image, but you don't have it on the base geometry. It was not showing it in the first method, but now you actually see that like the spoiler was added to the base geometry. Don't know if the projection is that good, but trust me, you can actually see these creases, these indents actually now trickling back to the geometry. And then you can plug it back into the thing, and you can start taking viewpoints from around this geometry based on your style input. So this solves kind of the two problems that we had, the fiction before physics. We uncoupled the sequential nature, because we can tackle the whole thing as one optimization problem. It can take into account a lot of your wishes, and then it will try to find an optimal solution that adheres to your constraints. And also, we actually can now have the geometry be updated by these image inputs. So, as the takeaway here is that basically the crux here was to actually use the structured latent space as this powerful representation for control generation, which you can add. You can play around with this. So that we arrived at an iterable, editable, constrained, image-driven, geometry-supported exploration method. And what it enables is that the client is then able to do a lot more faster iterations, fewer design to engineering loops, and have higher novelty or a higher creativity within the constraints that was set out. So like I said, we founded Datameister 2 years ago. We're now about a team of 14 people. We're bootstrapped. And we focus on developing these AI capabilities, typically for visual modalities and specifically 3D, the analysis and the generation of this. And we do this so that other companies can build a business around our AI capabilities. So feel free to talk to me during lunch. I'm here for 2 days.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.